Good evening. Stream on the break. Let us continue the session. Okay. So here we were discussing about the differentiation. Okay, the automatic differentiation has the benefit of providing gradient information that is accurate to working precision. So in contrast, the finite difference calculations provide only an approximation to the gradient with accuracy depending on the selected step size. And here actually we were discussing about the example of the boy, blindfolded boy, who is climbing uphill, and here the gradient was calculated based on the step size, and here an automatic differentiation has to be conducted, and it has the benefit of providing gradient information that is accurate to working precision. And in contrast, the finite difference calculations provide only an approximation to the gradient and with the accuracy depending on the selected step size. So suppose if the selected step size is increased, the accuracy will reduce, and if the selected step size is decreased, the accuracy will increase. And finally, some numerical simulations can provide analytic or semi-analytic gradient information directly. So here some numerical simulations can also be performed, and which will provide analytic or semi-analytic gradient information directly. Okay. So here, for example, please wait, I think, yeah, if the stream is running. Thank you for the patience. In contrast, finite calculations provide only an approximation to the gradient with the accuracy depending on the selected step size. And finally, some numerical simulations can provide analytic or semi-analytic gradient information directly. For example, analytic and semi-analytic gradient calculations can be implemented for linear finite element codes to provide computationally inexpensive gradient information for structural optimization application. Okay, so there is some example where we can take analytic and semi-analytic gradient calculations, and which can be used to implement linear finite element codes to provide computationally inexpensive gradient information for structural optimization applications. So the information can be prefetched so that it reduces the computational complexity, and thus it becomes inexpensive. Similarly, semi-analytic gradient calculations can be implemented efficiently in computational fluid dynamic codes, and this is one of the applications where we have used the gradient calculations. And as you have seen earlier, that there is the numerical noise involved in computational fluid dynamics. The general rule of thumb is to use the gradient provided by the analysis program if it is available. So actually there is a general rule of thumb, and what is the thumb rule here? It is to use the gradient provided by the analysis program. So a analysis program will find out the gradient, and from the information, the gradient information, it is possible to compute, or it is possible to perform the calculation. The gradient information obtained from the analysis code is typically obtained at a significant reduction in computation cost and is often more accurate than performing the finite difference gradient calculations. So actually we can reduce the computation cost by prefetching the data. That is, it obtains using the analysis codes. It obtains the gradient information, and from the gradient information, significant reduction in the computation can be done, and which will reduce the costs. Depending on the scenario, different search directions are required in equation number 2. So as you have seen in equation number 2, which actually shows the search direction. This is equation number 2. Let me mark this as equation number 2. This is equation number 2. Okay. So from equation number 2, as you can see that the x raised to q is equal to x raised to q minus 1 plus, sorry. So that is x raised to q is equal to x raised to q minus 1 plus alpha asterisk s raised capital S raised to q, and whereas capital S is the search direction, and this is what we are referring to now here. So the gradient information obtained from the analysis code is typically obtained at a significant reduction in computation cost and is often more accurate than performing the finite difference gradient calculation, and depending on the scenario, the different search directions. So here the search direction actually from the equation are required in equation number 2. So for unconstrained optimization problems or constrained optimization problems with no active or violated constraints, a search direction that will improve the objective function is desired. So here constraints എന്ന് പറയുന്നത് നമ്മൾ ഇവിടെ കണ്ടു. For example, if the boy is climbing up the hill and the fences are actually, there are 2 fences seen there, and actually if the boy is moving in the x direction to much extreme level, then there will be a fencing which blocks the boy from going further. Okay. And if he is moving in the y direction to a great extent, then there will be a blockage, or there will be a obstruction created by the fencing in that particular direction. So actually these are the constraints. Constraints actually mean the point up to which, or the limit up to which particular optimization can be performed. And here in constrained optimization problems with no active or violated constraints. So the constrained optimization problems may have active constraints or active with no active constraints or violated constraints. It may violate a constraint also. So so in a constraint problem, it has no active or violated constraints. So in that condition, we can say that the optimization has actually reached to the maximum, or the desired value, or which is the ultimate aim, and a search direction that will improve the objective of the function is desired. So here the search direction will improve the objective of function which is desired. So objective function, as you have seen in the first step, here we have the objective function, and which is f of x. So this is our ultimate aim, that is to finally find out or reach the goal function, or which is also called as the objective function. Okay, so further we can see that any search in the direction that will improve the objective function is referred to as a usable direction. So which is a usable direction? So any search direction that will improve the objective function is referred to as a usable direction. And for constrained optimization problems with one or more violated constraints, a search direction that will overcome the constraint violation is desired. So we have to have a search direction that will overcome the constraint violation desired. Okay. And for constrained optimization problems with one or more active constraints and no violated constraints, a search direction that is both usable and feasible is required. A feasible direction is any direction that will not violate the constraint bounds. So here actually, what is the feasible direction? For example, the same example we can take, the boy is climbing uphill, and here the feasible direction is only is any direction that will not violate the constraint bounds. Actually, which is the constraint bounds here means the fences. Okay. The different gradient based algorithms that exist differ mostly in the logic used to determine the search direction. Okay. The different gradient based algorithms, so we are discussing about gradient based algorithm that exist differ mostly in the logic used to determine the search direction. So we have to find out the search direction, and according to which we can calculate x raised to q. So actually the x raised to q value depends on the search direction. s raised to q. For one-dimensional search, there are many algorithms that will find the best step size, and generally any of these techniques can be combined with a particular gradient-based algorithm to perform the required one-dimensional search. So usually we have one-dimensional problems, one-dimensional gradient-based algorithm, and in such a one-dimensional search, there are many algorithms that will find the best step size, and generally any of these techniques can be combined with a particular gradient-based algorithm to perform the required one-dimensional search. So ഇവിടെ one dimensional എന്ന് പറയുന്നത് either in the x or y direction. If you have, for example, a particular case you want to discuss, then it means here the dimension means only in a particular direction, and in most of the cases we are using such a simple computation, or it reduces much of the computation complexity. Okay, so this is a direct method. It's also called as a direct method. And some of the popular one-dimensional search algorithm include the golden selection search, the Fibonacci search, and many variations of polynomial approximations. And the one-dimensional search algorithms include golden selection search. So that is one of the search algorithms. And next is the Fibonacci search. Then another is called as a polynomial approximation. So Fibonacci search was based on Fibonacci numbers, and the polynomial approximation based on polynomials. When gradient information is available, the Karush-Kuhn-Tucker KKT conditions can be used to determine if a constrained local optimum has been found. So actually in the gradient based method, a technique called as Karush-Kuhn-Tucker conditions can be used to determine the constrained local optima. The Karush-Kuhn-Tucker conditions provide the necessary condition for a local optimum and can be summarized as follows. So number one, the optimum design point x star must be feasible, and the optimum design point, the gradient of Lagrangian, must vanish. So let us see the Karush-Kuhn-Tucker conditions, and here delta fx asterisk plus sigma j equal to 1 to m lambda j delta gj x asterisk plus sigma k equal to 1 to p lambda m plus k delta into delta h k x raised of x raised to asterisk equal to 0. So this is this particular equation is called as the Karush-Kuhn-Tucker condition, and where the Lagrange multipliers lambda j is greater than or equal to 0, and lambda m plus k are unrestricted in sign. So these are the Lagrange multipliers. So as you can see in the equation, we have lambda j and lambda m plus k. These are respectively Lagrange multipliers, and the second one is these are the and here lambda m plus k are unrestricted in sign. So for each inequality constraint, lambda j gj of x equal to 0, where j is equal to 1 comma m. So these are the values allowable for j, that is interval 1 comma m. Then here note that the unconstrained problems, the Karush-Tucker conditions only require the gradient of the objective function to vanish at the optimum design point. So as you have seen the original objective function, it should vanish at an optimum design point, and so such a condition where in unconstrained problems we use the Karush-Tucker conditions, and only, and which requires the gradient of the objective function to vanish to a optimum design point. The Karush-Tucker conditions are useful for identifying a local optimum, but cannot indicate whether a global optimum has been found. There are several problems where it can be satisfactorily solved using the local optimum method, but other problems actually which does not fully solve, which cannot be fully solved using local algorithms, can be solved only using global algorithms. and these we are actually discussed these things earlier. So there are two optimization algorithms. Initially we have discussed about the global optimization and the local optimization. So these are the algorithms available, the local algorithms and the global algorithms. So this is where we are discussing. So here continuing, note that the unconstrained for unconstrained problems, the Karish-Kuhn-Tucker conditions only require the gradient of the objective function to vanish at an optimum design point. The Karish-Kuhn-Tucker conditions are useful for identifying a local optimum, but cannot indicate whether a global optimum has been found. So this is one of the features we Karish-Kuhn-Tucker. The feature is it is useful for identifying a local minimum, but it cannot indicate whether a global optimum has been found. So in the next method we use Newton's method. So the second method, in another method, is called as the Newton's method. So in Newton's method, one of the classical gradient based optimization algorithm is the Newton's algorithm. So this is one of the gradient based optimization algorithms, and it is also called as the classical gradient based optimization algorithm because of its popularity, and it's generally used in many problems. And Newton's algorithm is an unconstrained algorithm that is derived from the second order Taylor series expansion of the objective function about an initial design point x raised to 0. So the Newton's method depends on the second order Taylor series expansion, and here we are taking the initial design point as x raised to 0. So here as initially we have pointed out that x is a vector. So x is a vector, f of x approximately equal to f of x raised to 0, which is the initial design point, and plus delta f of x raised to 0 transpose x minus x raised to 0 plus 1 by 2 x minus x raised to 0 transpose h x raised to 0 into x minus x raised to 0. So actually it is in the matrix form, and we are taking the transpose of this, and we can say that we have taken transpose of x raised to 0 and x minus x raised to 0, and which are actually called as the Hessian matrix. So here where h of x raised to 0 is called as the Hessian matrix that contains the second order gradient information of the objective function, and differentiating equation number 4 with respect to x and setting the result equal to 0 according to the Karish-Kuhn-Tucker conditions results in the following update formula for the current design point. That is, x is equal to x raised to 0 minus h into h of x raised to 0 inverse delta f of x raised to 0. So here note that in the classical form Newton's method makes use of a fixed step size of 1. So we are using a fixed step size of 1, and no one dimensional search is required, and the search direction is only provided by minus h of x raised to 0 inverse delta f of x raised to 0. So this particular minus h of x raised to 0 inverse delta f of x raised to 0 is called the step size, and it is a fixed step size, that is 1, and the search direction, the search direction is provided by minus h of x raised to 0 inverse into delta f of x raised to 0. Newton's method has a quadratic rate of convergence and requiring only one single step, that is with the step size equal to 1, to obtain the optimum for any positive definite quadratic function. In practice, the method is modified to include one dimensional search that improve both the efficacy and the robustness of the method. So here Newton's method is one of the important techniques which solves several problems, and it is one of the popular optimization algorithm. And here we can see that in the Newton's method has a quadratic rate of convergence. So here we can see that a particular function diverges or converges, and here it converges at a quadratic rate. Here in the case of a Newton method, we can see that the function converges at a quadratic rate, and requiring only a single step. It requires only a single step, and the step size is equal to 1 to obtain the optimum of any positive definite quadratic function. And in practice, the method is modified to include one-dimensional search that improve both the efficacy and the robustness of the method, and improves the this step. Taking this step size, it improve in practice the method is modified to include one-dimensional search that improve the efficacy and robustness of the method. So initially we have seen in the earlier gradient algorithms, we are using a one-dimensional search, whereas here this doesn't require a one-dimensional search. It can have several dimensions, and although method has a quadratic convergence rate which is highly desirable, the computational cost associated with obtaining the second order gradient information in the Hessian matrix makes the method impractical in most cases. As a result, most gradient based methods make use of the first order gradient information only. So you can see that the neglecting the second order term, we use only the first order gradient information. So here, as a result, most gradient based methods make use of only the first order gradient information. So next we see the unconstrained optimization. So far we have seen the constrained optimization, where we have constraints or the limits. So in the next we will discuss about unconstrained optimization. So for unconstrained problems, two very popular methods are the Fletcher-Reeves and the Broyden-Fletcher-Goldfarb-Shano BFGS methods. So the two methods which are very popular are, so here we are discussing about unconstrained optimization, and the two popular methods are Fletcher-Reeves and Broyden-Fletcher-Goldfarb-Shano BFGS methods. The Fletcher-Reeves method makes use of conjugate search directions. The method is referred to as conjugate gradient method to reach the optimum. So it uses the Fletcher-Reeves method uses a conjugate method to reach the optimum. So the stream is running anyway. Yes, it is running. So these are the two very popular methods of Fletcher unconstrained optimization. The two popular methods of unconstrained optimization is one is Fletcher-Reeves and the second one is Broyden-Fletcher-Goldfarb-Shano, that is BFGS methods. The Fletcher-Reeves method makes use of the conjugate search directions, and here the method is referred to as a conjugate gradient method, and this method is referred to as a conjugate gradient method to reach the optimum. So Fletcher-Reeves method makes use of conjugate search directions, and the method is referred to as conjugate gradient method to reach the optimum. Okay. The conjugate search directions are created using information gained from previous design iteration. So here the conjugate search directions are created using information gained from the previous design iteration. So actually here we are conducting a previous design iteration. In the previous design iteration, the information is gained and obtained, and it is used to create the conjugate search direction. And this method works very well with very well and will theoretically minimize a quadratic function in n or fewer iterations. It has the added advantage of having a small computer memory requirement. So here the method works very well. Actually, this method is a very good method. That is Fletcher-Reeves method. We are discussing about Fletcher-Reeves method, and it works very well and will theoretically minimize a quadratic function in n or fewer iterations. It has an added advantage of having a small computer memory. Okay. The BFGS method is part of family of methods known as the variable metric method that makes use of information gained from the previous n iteration to find a new search direction. Numerical experiments indicate that BFGS method is the most efficient variable metric method, and the BFGS method creates an approximation to the inverse of Hessian matrix h of x raised to x inverse in equation number 5. So this method, the BFGS method, create an approximation to the inverse of the Hessian matrix, okay, as seen in the equation. So here this is the Hessian matrix in equation number 5, right. So this approximation is updated after each design iteration with the first order gradient information from that iteration. Since only an approximation of the inverse of the Hessian matrix is used, the method is known as quasi-Newton method. Mathematically, the BFGS method is considered superior to Fletcher-Reeves method, but has the drawback of requiring substantially more computer memory to store the approximate inverse of the Hessian matrix. So actually it requires computer memory to store the approximate inverse, as you can see here, of the Hessian matrix. So it requires the storage of the inverse of the Hessian matrix. So hence it requires more memory, computer memory, and this is one of the drawbacks of the BFGS method as compared with the Fletcher-Reeves method. Constraint optimization. So for constraint optimization problems, two approaches are considered here. The first is known as the sequential unconstrained minimization technique, SUMT. So SUMT stands for sequential unconstrained minimization technique approach. A comprehensive overview of the approach is provided in Fiacco and McCormick 1968. So this is a well-known work of Fiacco and McCormick. So in which it explains about sequential unconstrained minimization technique, SUMT. And the second as the direct or constraint methods. The SUMT approach solves the general constraint optimization problem by converting it to an equivalent unconstrained problem. This equivalent unconstrained problem is then solved using any one of the unconstrained algorithms already discussed, and the SUMT approach obtains an equivalent unconstrained problem by penalizing the original objective function for any constraint violations, and the penalized objective function is obtained from fp x comma p, fp of x comma p equal to f of x plus rp into p of x. So actually if we have an unconstrained problem, okay, sorry, okay, suppose here we are discussing about a constraint optimization. Actually the SUMT approach here, the SUMT method, which is a sequential unconstrained minimization technique, here the constraint optimization is converted to an unconstrained optimization. So in the SUMT approach, here we convert the constrained optimization to the unconstrained optimization algorithm, and it is solved using any of the techniques discussed earlier with unconstrained optimization. So ഇവിടെ നമ്മൾ അൺകൺസ്ട്രെയിൻഡ് ഒപ്റ്റിമൈസേഷൻ്റെ ഡിഫറെൻറ്റ് അൽഗോരിതംസ് നമ്മൾ ഡിസ്കസ് ചെയ്തിരുന്നു. ന്യൂട്ടൺസ് മെത്തേഡും ഒക്കെ ഇതിനകത്ത് പെട്ടതാണ്. ഇവിടെ നമ്മൾ ഇതാണ് ഇവിടെ അൺകൺസ്ട്രെയിൻഡ് ഒപ്റ്റിമൈസേഷൻ എന്ന് പറയുന്നത്. അതിൽ നമ്മൾ ഡിസ്കസ് ചെയ്തതാണ് ഫ്ലെച്ചർ റീവ്സ് മെത്തേഡും ബ്രോയ്ഡൻ ഫ്ലെച്ചർ ഗോൾഡ്ഫാബ് ചാനോ മെത്തേഡ്, BFGS മെത്തേഡും. ഓക്കെ. So there actually in the unconstrained method, so here when you are using a constrained method, the optimization method, such as a SUMT method, we are converting the SUMT method to which is a constrained optimization to an unconstrained optimization method, and we are solving it using any of the unconstrained optimization algorithms. And this equivalent unconstrained optimization problem is solved using any of the unconstrained algorithms discussed earlier. And the SUMT approach obtains an equivalent unconstrained problem by penalizing the original objective function for any constraint violation. So, if there is any constraint violation and a penalizing function, there will be a penalizing function and it creates a penalizing value, and the original objective function will be modified based on the penalizing value. So, how that is done is it can be evident from the following equation. The penalized objective function is obtained from fpx comma rp equal to f of x plus rp p of x. So, this is the original objective function f of x. F of x is the original objective function plus the penalized function, that is rp p of x, gives the function fp of x comma rp, where rp stands for the penalizing factor or the value of the penalizing factor. Here fp of x refers to the penalized objective function and rp is the penalty parameter. So, actually it is a parameter or penalty parameter, and p of x to the penalty function, and p of x as shown here is the penalty function. The classical approach is to keep the rp constant for a complete unconstrained minimization of the cycle of fp, and once the unconstrained optimization solution is found, the value of the penalty parameter rp is increased and the unconstrained optimization cycle is repeated. So, here fp as it is evident, it is the unconstrained minimization cycle. Okay. So, actually xp of x refers to a penalized objective function where rp is the penalty parameter and p of x is the penalty function. The classical approach is to keep rp constant for a complete unconstrained minimization cycle of fp, as referred to here. Fp refers to the penalized objective function. Once the unconstrained optimum solution is found, the value of the penalty parameter rp is increased. So, we can increase the value of the penalty parameter rp. As you can see in this equation, we can increase the value of rp, and the unconstrained optimization cycle is repeated, and we can repeat the unconstrained optimization cycle. The result is a sequential progress towards the constrained optimum. So, finally, it approaches the constrained optimum. The process is terminated when the objective function value converges between successive unconstrained optimization cycles. So, finally, we can see that the objective function value converges between a successive optimization cycle. So, here the aim is to convert the unconstrained optimization to the constrained optimization. Sorry, the aim is to convert the constrained optimizations to unconstrained optimization, and we can see that between successive unconstrained optimization cycle, the object function value converges, and there are many different penalty functions, and one function is the exterior called quadratic penalty function. So, the function the penalty function, as you can see here the penalty function is denoted by fp of x. So, fp of x, and the quadratic penalty function here, this is fp of x. So, this is given by p of x. P of x is the penalty function, and here it fp of x refers to the penalized objective function, where the penalty function is p of x. So, here we are referring to the penalty function p of x, and the quadratic penalty function p of x is equal to sigma j equal to 1 to m max of 0 comma gj of x the whole square plus sigma k equal to 1 to l h of hx x square. So, this is called as this function is called as the penalty function, and this here p of x is defined as the summation max of 0 comma gj x gj of x whole square plus sigma k is equal to 1 to l hk x square. The exterior penalty function approaches the constraint optimum for the infeasible region of the design space. So, here the exterior penalty function, so which is here, this is called as the exterior penalty function, approaches the constrained optimum, and it reaches the constrained optimum for from the infeasible this from the infeasible region of the design space. So, actually design space here means the two-dimensional space where the problem we are discussing, the constraint problem we are discussing is to be applied. There are also interior and extended interior penalty functions available that approach the constraint optimum for the feasible region of the design space. Okay, so there are also interior and extended interior penalty functions. Penalty functions can be two types. One is the interior and the second is the extended interior penalty function, and that is available that approach the constraint optimum from the feasible region of the design space. Okay, and the biggest drawback of this method is related to the value of the penalty parameter. So actually this depends upon the penalty, the accuracy depends on the penalty parameter. As you can see, this here is the penalty parameter RP. Here RP is refers to the penalty parameter, and this depends on RP. So the penalty parameter has a significant influence on the performance of the algorithm, but is problem dependent. And often must be set extremely large to obtain satisfactory results, which may lead to numerical ill conditioning. So it has a drawback of that it may lead to numerical ill conditioning. The augmented Lagrange multiplier method is one of the methods that overcomes this limitation by creating a penalty function based on the Lagrangian and defines penalty parameters based on estimates of the Lagrange multipliers. So here one of the solution is to use Lagrange multiplier, and by using Lagrange multiplier, this limitation of creating penalty function can be, or there is some due to the numerical ill conditioning. This is one of the limitations of using the penalty parameter. So as the value of the penalty parameter increases, you can see there is a numerical ill conditioning, and which can be overcome by using the Lagrange multiplier. The augmented Lagrange multiplier method has the advantage of achieving satisfaction for a finite value of RP, and is less sensitive to the selected RP value. So here this is called as the augmented Lagrange multiplier. Augmented Lagrange multiplier means the modified Lagrange multiplier method, and has an advantage of achieving exact constraint satisfaction for a finite value of RP. So where RP is the penalty parameter, and is less sensitive to the selected RP value. The SUMT methods have become less popular as the direct or the constrained methods became more mature and efficient. So as the direct method is more popular and is much mature when compared with the SUMT methods. But today the gradient based technique of choice for constraint optimization problem is the direct methods, which will be discussed in this in the next session. So there is one interesting area where SUMT methods are making a comeback, and that is for very large scale in terms of number of design variables optimization problems. So this is one of the interesting areas of the SUMT methods, and that's why it's making a comeback. That is for a very large scale. So in the case of very large scale optimization problems. An example of is the commercially available big dot algorithm from Van der Plaats Research and Development, Van der Plaats 2004, which can be used to solve constraint optimization problems with hundreds and thousands of design variables. So if you are increasing the number of design variables, where we have seen the earlier equation, small n is the number of design variables, and if you are increasing the value of n, there is a defined design number of design variables, it finds more application. And SUMT method is used in such areas, in problems where there is a large scale of the design variables. The direct methods directly solve the linear constraint optimization problem. Equation 1. So actually referring back to the equation number 1. So this is equation number 1 we were referring to originally. So this is equation number 1, where f of x is the objective function, gj of x is the inequality constraint, and hk of x is the equality constraint function, and these are the limits, or which can be called as the lower bounds and upper bounds, or the constraints, and also referred to as the side constraints. So coming back, in the direct methods directly solve the nonlinear constraint optimization problem in equation number 1. So the equation number 1 is an example of a nonlinear constraint optimization problem, and many different constraint optimization algorithms are available. So direct methods directly solve the nonlinear constraint optimization problems and of equation number 1, and many different constraint optimization algorithms are available to solve. Okay. So in engineering, 3 algorithms that are commonly encountered are the sequential linear programming, which is the SLP algorithm. SLP stands for sequential linear programming. Then the modified method of feasible direction, MMFD. So the MMFD, otherwise called as the modified method of feasible directions, and the sequential quadratic programming, SQP algorithm. So next is the sequential quadratic programming called the SQP algorithm. The SQP algorithm simplifies the general nonlinear constraint optimization problem to an equivalent linear problem by creating linear approximation to the objective and the constraint function about the current design point. So here the SLP algorithm simplifies the general nonlinear constraint optimization problem to an equivalent linear problem by creating a linear approximation to the objective and the constraint functions. As you see the original equation number 1, the objective function and the constraint function. So the aim is to solve or simplify the solution for finding the objective function and the constraint function, and using the current design point. And using an appropriate algorithm, the optimum solution for these linear approximation is found, and the resulting design point is evaluated. Okay. So using the appropriate algorithm, the optimum solution for this linear approximation is found, and the resulting design point is evaluated. So design point is evaluated, and by using linear approximation we can use the optimum solution for this linear approximation in the algorithm. So a new set of linear approximation is constructed about the newly evaluated design point, and the process is repeated until convergence. So here the ultimate aim is to reach the convergence. So finally at the convergence we can find out the objective function, and here the new set of linear approximation is constructed about this newly evaluated design point. Okay. So by the newly evaluated design point is used to define a new set of linear approximation, and or it's used to a new set of linear approximation is constructed. The method is very sensitive to move limits and may or may not always find a feasible solution. As a result, it is generally considered inferior to the MMFD and the SQP algorithm. So here comparing SLP algorithm with MMFD and SQP, we may say that the result here it is inferior to MMFD and SQP methods algorithms. The MMFD algorithm is based on modification of the original method of the feasible direction algorithms, and MMFD is actually based on the modification of the feasible direction algorithm. The modification provides a search direction. The modification provides a search direction that follows the active constraint bounds rather than moving inside the feasible region towards the optimum. So here the modification provides a search direction that follows the active constraint bounds towards the optimum. The MMFD algorithm is extremely robust, has the property of quickly finding the feasible design space, and is widely used in the structural optimization. So there are several structural optimization problems where MMFD algorithm can be used, and it is extremely robust, and it has the property of quickly finding the feasible design space. So the SQP algorithm is probably the most popular direct algorithm for engineering optimization application. Both comparing MMFD and SQP is probably the most popular direct algorithm for engineering optimization applications. This algorithm finds a search direction by solving an approximate problem based on the quadratic approximation of the objective function and the linear approximation of the constraint function. So here the algorithm finds a search direction. So we initially in equation number 2 we have seen the search direction, and that is by solving an approximate problem based on the quadratic approximation of the objective function and the linear approximation of the constraint functions. One of the new search direction is determined. A penalty function is typically used to determine the step size in the obtained search direction. So in the obtained search direction, the penalty function is typically used to determine the step size, and once that is determined, that the search direction can be found out. Then the new design point obtained from the combining the search direction and the optimal step size, as in equation number 2, is that evaluated as a new design point, and the process is repeated until convergence. So that can be seen in the equation number 2. How this can be used in equation number 2, where which involves the direction. Okay, here we can see that S is the search direction, and the step size is alpha raised to asterisk. This is the step size, alpha raised to asterisk. So a new set of linear approximation is constructed about the newly evaluated design point, and the process is repeated until convergence. So the method is very sensitive to move limits and may not always be find a feasible solution. As a result, it is generally considered inferior to MMFT and SKP algorithms. Actually we are discussing slightly beyond this point. Yeah. The MMFD method is extremely robust and has the property of quickly finding the feasible design space, and is widely used in structural optimization. The SQP method is probably the most popular method. So among MMFD and SQP is probably the most popular direct algorithm for engineering optimization application. And this algorithm finds a search direction by solving the approximate problem. Excuse me, 1 minute. Pardon. Stop is open. അതെ പറയുന്നു അപ്പോൾ ഏതായാലും അവിടെ അഡ്മിഷൻ എടുക്കുകയാണ്. Okay, okay, okay. അപ്പോൾ എന്താ പറഞ്ഞേ? ആ ആ ആ വിട്ടോ, വണ്ടിയിൽ പറഞ്ഞു കേട്ടോ, തിരിച്ച്. ആ ആ ആ ഓക്കെ ഓക്കെ ഓക്കെ. ശരി 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 ശരി. അപ്പം ഞാനൊരു ക്ലാസ്സിലാണ്, ഓൺലൈൻ ക്ലാസ്സിലാണ്, കുറച്ച് കഴിഞ്ഞ് തിരിച്ച് വിളിക്കാം. ഓക്കെ, ശരി. Sorry for the break. Let me continue. So here SQP algorithm is probably the most popular direct algorithm for engineering optimization applications, and this algorithm finds a search direction by solving an approximate problem based on the quadratic approximation of the objective function and the linear approximation of the constraint function. So here the two things we are already discussing is, one is objective function and second is the constraint function. And here this algorithm, that is SQP algorithm, finds a search direction by providing approximate problem based on quadratic approximation of the objective function and a linear approximation of the constraint function. Once the new search direction is determined, a penalty function is typically used to determine the step size in the obtained search direction. And the new design point obtained from combining the search direction and the optimum step size using equation number 2. So as you have seen the earlier equation, in equation number 2, we are finding the step size, we are applying the step size, then is then evaluated as the new design point, and the process is repeated until convergence. So finally we are repeating the steps until we reach the convergence. Although a penalty function is typically used to perform the one-dimensional search, a new algorithm by Fletcher and Leifer 2002 provides an interesting alternative where a bi-objective formulation is used to replace the one-dimensional search with a filter. So here instead of a single one-dimensional search, a bi-objective formulation is used. So the other direct methods that may be encountered, which includes gradient projection and the generalized reduced gradient methods. So there are other direct methods also which may be encountered, which can be used, which may be encountered in the optimization techniques, and which includes the gradient projection method and the generalized reduced gradient methods. An interesting collection of relatively new gradient based algorithms by Schneemann and his co-workers is contained in Schneemann 2005. It's a paper by Schneemann, and these algorithms were developed specifically to deal with the real world problems where expensive function evaluations, numerical noise, discontinuities, local minima areas in the design space where the functions are not defined and large values of design variables are encountered. Okay. The collection consists of algorithms that require only first order gradient information and that do not rely on one dimensional search. So actually, as you can see here, it uses a bi-objective formulation instead of a one-dimensional search. And the algorithms for constrained and unconstrained optimization, approximation methods, and methods for global unconstrained optimization are presented. So here, so far we have seen different methods in based on the local constrained optimization, and here we are going to discuss about algorithms for constrained and unconstrained optimization and the approximation methods and methods for global unconstrained optimization. So in the non-gradient based methods, so this is one of the non-gradient based methods. Earlier we have used the gradient based methods, which is simple, straightforward, whereas we have another method which is non-gradient based. So the discussion of local search techniques would not be complete without also mentioning the existence of non-gradient based local search algorithms. Popular examples of non-gradient based methods are Powell's method, Powell's method is one of the method which does not use a gradient. So, and the Nelder-Melt simplex algorithm, which also does not use a gradient. Both algorithms are capable of solving non-linear unconstrained optimization problems. Powell's method is based on the concept of conjugate direction, while the Nelder-Melt algorithm makes use of simplex and a set of symbol rules that reflects the worst vertex through the centroid of the simplex. So, these two actually, Powell's method and the Nelder-Mead method algorithm does not use a gradient technique. It is a non-gradient based algorithm. So, global optimization algorithms. Stream on the continue. Yes, it is continuing. So, global optimization algorithms. The issue of local versus global optimization has already been discussed briefly in the previous sections. So, we have discussed earlier about local optimization and global optimization and the comparison, and many problems have multiple optima with a simple one variable function shown in the figure below. So, this can have many problems where they have multiple optima values. So, this is a one dimensional multimodal function, and here you can see the objective function f of x, and this is the vector x, and you can have values for different values of x and find out f of x for different values of x. So, you get a plot here. This is the shape of the plot, and you can see that there is a minima at x is equal to plus or minus 1. So, this is the value plus or minus 1. So, x is equal to plus or minus 1. So, this you can see the x value for minus 1, this is the value for plus 1, and these are the points corresponding to plus or plus 1, and this is for minus 1, plus 1 and minus 1. And the figure we can see that the minima at approximately equal to plus or minus 1 represents the local or relative minima. So, these values are the local, called as the local minima, while at x equal to 0. So, this point where a particular value where x is equal to 0.0 or 0 represents the global or the absolute minimum. So, this point refers to the global minimum. So, where x is equal to 0. So, previously we have seen what is meant by global minimum. When we have x is equal to 0, we get the global minimum. So, here the minimum is at x is equal to 0 represents the global or absolute minimum. All 3 points satisfy the Karush-Tucker conditions. So, all these points, 3 points, these are the 3 points we have discussed. One is at plus minus 1, x equal to minus 1, the other is at x equal to plus 1, and the other one, third one is at x equal to 0. And these 3 points satisfies the Karush-Tucker conditions previously discussed. The local algorithms discussed so far will converge on any of these 3 points depending on which one is encountered first. And when using local optimization algorithm, a simple approach for dealing with multiple local minima in the design space is to use a multi-start approach. And these approaches can be seen in Haim et al. 1999 and Coax et al. 2001. So, here the local algorithms discussed so far will converge on any of these 3 points, that is here, here or here, and depending on which one is encountered first. So, which one is encountered, depending on which one is encountered first, that will converge. And when using a local optimization algorithm, so a simple approach for dealing with the multiple local minima in the design space is to use multi-start approach. Okay. So, in the multi-start approach, the multiple local searches are performed, each starting from a different starting point. Often a design of experiment DOE approach is used to generate the set of starting points. So, how these starting points are generated? This is from the design experience DOE, design of experiments. Okay. So, global optimization algorithms provide us a much better chance of finding the global or near global optimum, and the local algorithm discussed so far than the. So, here actually we can see that local algorithms may not solve many problems where we require the global optimization. So, in the global optimization algorithm provides a much better chance of finding the global or near global optimum. So it is important to note that no algorithm can guarantee convergence of a global optimum in the general sense, and it may be more accurate to refer to these algorithms as having global properties. As you can see that as compared with the local algorithms, a global algorithm is shown to have greater accuracy, especially when the we are using a large number, or we have a large number of inputs. The global optimization algorithms may be classified either as evolutionary algorithms or deterministic algorithms. The global optimization algorithms may be classified either as evolutionary algorithms or deterministic algorithms. So let us see next what is meant by evolutionary algorithms. So in the evolutionary algorithm, optimization algorithm have a very popular, these have become very popular in the last decade or two. So there is a method of called the evolutionary optimization algorithm, which has become very popular in the last decade or two. And unlike the local technique, where a single design point is updated, typically using a gradient information from one iteration to the next, these algorithms do not require any gradient information and typically makes use of a set of design points, generally referred to as a population, to find the optimum design. So earlier in the local algorithms, we have optimization algorithms. We have seen that it is based upon gradient information. So the gradient has to be estimated or evaluated, whereas this does not. The evolutionary algorithm doesn't require any gradient information, and it typically makes use of set of design points. So by using a set of design points, it can proceed, and we can see that the set of design points is generally referred to as a population. So this is the set of design points is called as a population. These methods are typically inspired by some phenomena from nature and have the advantage of being robust and having an increased chance of finding a global or near global optimum, being easy to implement and being well suited for discrete optimization problems. So we can see that these methods, the methods discussed here, the global optimization is inspired from some phenomena from nature and have the advantage of being extremely robust, having an increased chance of finding a global or near global optimum, and being easy to implement and being well suited for discrete optimization problems. So it's actually there are problems where the optimization problems might be discrete. The values used might be discrete. So in the initial case where you have seen the f of x of the objective function, and which is evaluated from the values or the values of x and y, and these values can be discrete or maybe having continuous values. So in the case of discrete optimization problems, we are using discrete values, and we can see that this becomes complex. The big drawbacks associated with these algorithms are high computational cost, poor constraint handling abilities, problem specific parameter tuning, and limited problem size. So these are the big drawbacks associated with these algorithms. That is high computational cost, poor constraint handling abilities, problem specific parameter tuning, and a limited problem size. Currently, two of the most popular evolutionary algorithms are the more established genetic algorithm, so which is one of the important algorithm, genetic algorithm GA, as according to Holland 1975, which was inspired by Darwinian principle of survival of the fittest, and the particle swarm optimization, or PSO, which is called PSO, particle swarm optimization, by Kennedy and Eberhard, and which is based on a simplified social model. So we can see later on see the examples of a socialized social model, and here this called the social model is called the particle swarm optimization. And in the evolutionary algorithms, there are the most popular evolutionary algorithms are, one is the genetic algorithm GA, and second is the particle swarm optimization, and both are inspired from nature. So One is inspired from Darwinian principle of survival of the fittest, which is the genetic algorithm, whereas the particle swarm optimization is also inspired from nature from the social model. And we can say that later on we can see that the ant optimization colony and the, the bee optimization is also inspired from the same social model, and which are examples. So other algorithms that fall into these evolutionary programming, genetic programming, and differential evolution, and simulated annealing, then taboo search, and harmony search, and these are the different other algorithms other than the genetic algorithm and the particle swarm optimization algorithm. The basic steps The basic steps in the genetic algorithm are illustrated in the figure 3 below. The first step is to create a random initial population. So we can see the various steps of creating population here. This is the population. We can see 4 kinds of population, and this is the rank of the population. So this is the rank of the first population 4, then this is the rank of the second population, which is 1, and this is the rank of the third population, which is 3, and rank of the fourth population is 4. Then the 2. Then the children are formed by the various combination of the populations. So here the first child is formed from the population, here this one, that is the population having rank 2 and the population having rank 1. So this will be random combinations of the different populations. So we can see here the going back, we can see that the basic steps of a genetic algorithm are in the figure as seen. The first step is to create a random initial population. So there is a random initial population because it can be from any parent. So the combination can involve any of the parents. So the combination can involve any of the parents. Then the first step is to create a random initial population. Typically the population size does not change during the optimization study. So here the population size does not change during the optimization study. The population is then ranked. So there is a ranking as seen in the figure based on the fitness or the objective function of each individual, and the parents are randomly selected for reproduction. So the parents here are selected randomly for the reproduction. The parent designs are selected in such a way that the higher ranked fitter individuals have higher probability of being selected. So the higher rank, so as you can see in the figure, the higher ranked population has the higher chance of being selected. Okay, so when the children are formed, the chances that the higher rank population is selected more often. The parent designs are selected in such a way that the higher ranked individuals have a higher probability of being selected, and the next generation is then filled with children designs created by randomly mixing the selected parent designs in a process known as crossover. So in a process known as crossover, the children designs are created by randomly mixing selected parent designs. The new generation is again ranked, and the process is repeated until convergence. So actually the new generation means the offspring or the children is again ranked, and this is again ranked, and the process is repeated until the convergence. So until convergence the process is repeated. Figure 3 illustrates the process of an initial population consisting of only 4 individuals. So here in the figure 3, as you can see, there are the 4 parents the initial population. The population has there are 4 types of population: 1, 2, 3, 4, and these are the various ranks associated with the population. And the selection is made based upon the rank of the population. In contrast, the PSO models have the behavior of, for example, a swarm of bees. So actually here a swarm of bees means a colony or a group of bees, and here the bees are searching for food, and a different problem is an ant colony. So here these are having some social characteristics. നമുക്കറിയാം ഈ പറയുന്ന തേനീച്ചകൾക്ക് ഒരു പ്രത്യേക സ്വഭാവമുണ്ട് അല്ലേ, അത് ഭക്ഷണം ശേഖരിച്ച് വെക്കുന്നതാണ്. അതായത് മഴക്കാലത്ത് അതിന് സുരക്ഷിതമായി ജീവിക്കാനായിട്ട്, സുരക്ഷിതമായി താവളത്തിൽ ഇരിക്കുവാനും ഭക്ഷണം തേടിപ്പോകാനായിട്ട് സാധിക്കത്തില്ല. മഴക്കാലത്ത് ഭക്ഷണം തേടിപ്പോകാൻ സാധിക്കാത്തതുകൊണ്ട് വേനൽക്കാലത്ത് അത് ധാരാളം ഭക്ഷണം, അതായത് തേനിൻ്റെ രൂപത്തിൽ അത് സ്വീകരിക്കുകയും അത് പിന്നെ പൂവിൽ നിന്ന് തേൻ എടുക്കുകയും ആ തേനിൻ്റെ രൂപത്തിൽ അത് സ്റ്റോർ ചെയ്ത് വയ്ക്കുകയും ചെയ്യുന്നു. അപ്പം അത്തരത്തിൽ അതൊരു ക്യാരക്ടറിസ്റ്റിക്സ് ആണ്, ഒരു നേച്ചറാണ്, ബീസിൻ്റെ ഒരു നേച്ചറാണ്. അപ്പോൾ അത്തരത്തിൽ ഇവിടെ നേച്ചറിൽ നിന്നും എവല്യൂഷണറി അൽഗോരിതംസ് എല്ലാം നേച്ചറിൽ നിന്നും ഇൻസ്പയർ ചെയ്തിട്ടുള്ളതാണ്. അപ്പോൾ അതുകൊണ്ട് അത്തരത്തിലൊരു ക്യാരക്ടറിസ്റ്റിക്സ് ഇവിടെ ഈ പറയുന്ന എവല്യൂഷണറി അൽഗോരിതംസ് ഉണ്ട്. അപ്പോൾ ഇവിടെ ഈ പറയുന്ന ബി ആണെങ്കിലും ആൻഡ് ആണെങ്കിലും ദീസ് ആർ റെപ്രസെൻറ്റിങ് ഓൺലി പാർട്ടിക്കിൾസ്. സോ ഇതൊക്കെ ഒരു ആർട്ടിഫിഷ്യൽ പാർട്ടിക്കിൾസ് അല്ലെങ്കിൽ ഇത് നാച്ചുറലായിട്ടുള്ള ഒരു എന്താ പറയുക, ഒരു ഇൻസെക്റ്റിനെ ബേസ് ചെയ്തിട്ടാണ് പറയുന്നതെങ്കിലും ഇതിൻ്റെ ഇക്വലൻ്റ് ആയിട്ട് നമ്മൾ ഈ ഒപ്റ്റിമൈസേഷൻ അൽഗോരിതത്തിൽ ഇതിനെയൊക്കെ നമ്മളിപ്പോൾ ഫോർ എക്സാമ്പിൾ ഒരു പാറ്റേൺ റെക്കഗ്നിഷൻ പ്രോബ്ലം ആയിക്കോട്ടെ, അല്ലെങ്കിൽ അത്തരത്തിലുള്ള ഏതെങ്കിലും ഒരു ഇപ്പം ഡേറ്റ മൈനിങ് റിലേറ്റഡ് ഒരു ആപ്ലിക്കേഷനോ എവിടെയൊക്കെ പോപ്പുലേഷൻ വരുന്നുണ്ടോ അവിടെയൊക്കെ ഈ തരത്തിലുള്ള ഈ പറയുന്ന നാച്ചുറൽ ആയിട്ടുള്ള ഈ പറയുന്ന ഫിനോമിനൻ, അതായത് സ്വാം ഓഫ് ബീസ് ആണെങ്കിലും ആൻഡ് കോളനി ആണെങ്കിലും അതിൻ്റെയൊക്കെ ആ ഒരു ഫീച്ചേഴ്സിൽ നിന്ന് ഇൻസ്പയർ ചെയ്തിട്ടാണ് അൽഗോരിതംസ് ഫോം ചെയ്തിട്ടുള്ളത്. അപ്പോൾ അത്തരത്തിലുള്ള അൽഗോരിതംസിനെ നമ്മൾ പിന്നെ ഇവിടെ പ്രത്യേകിച്ച് പറയുന്നത് these are actually PSO, which stands for the particle swarm optimization. So here actually particle in the sense it can be any particle based on say for example pattern recognition. It can be a particle in a pattern recognition. അവിടെ പാർട്ടിക്കിൾസ് എന്ന് ഉദ്ദേശിക്കുന്നത് അവിടെയുള്ള പിക്സൽസിനെയാണ്. ഇത്തരത്തിൽ ഒരു സോഷ്യൽ ബിഹേവിയർ നമുക്ക് സ്റ്റഡി ചെയ്യാൻ പറ്റും. ഫോർ എക്സാമ്പിൾ ഒരു ഗ്രൂപ്പ് ഓഫ് ഇൻഡിവിജ്വൽസ്, ഫോർ എക്സാമ്പിൾ യു ഹാവ് എ പെർട്ടിക്കുലർ ഹാൾ, ഒരു വലിയ ഹാളിൻ്റെ ഉള്ളിൽ കുറേ ആൾക്കാർ സ്പ്രെഡ് ചെയ്തിരിക്കുകയാണ്. അപ്പോൾ ഇവിടെ ഒരു സോഷ്യൽ ഗ്യാതറിംഗ് ആണ് സത്യത്തിൽ. ഈ ആൾക്കാർ റാൻഡമായിട്ട് അങ്ങോട്ടും ഇങ്ങോട്ടൊക്കെ മൂവ് ചെയ്യാണ്. അപ്പോൾ ഈ ഗ്രൂപ്പിനെ നമ്മൾ സ്റ്റഡി ചെയ്യാമെന്ന് വിചാരിച്ചു. നമ്മൾ ഈ പാർട്ടിക്കിൾ സ്വാം ഒപ്റ്റിമൈസേഷൻ യൂസ് ചെയ്തിട്ട് ഈ ഒരു ഗ്രൂപ്പ് ഓഫ് എന്താ പറയുക ഹ്യൂമൻ ബീയിങ്സിനെ സ്റ്റഡി ചെയ്യുകയാണ്. അങ്ങനെയുണ്ടെങ്കിൽ ഓരോ ഹ്യൂമൻ ബീയിങ്ങിനെ അവിടെ ഓരോ പാർട്ടിക്കിളായിട്ട് അസ്യൂം ചെയ്യാം. ഇതിൻ്റെ ഒരു റെപ്രസെൻറ്റേറ്റീവ് ഇമേജോ അല്ലെങ്കിൽ അതിൻ്റെ ഒരു വീഡിയോ നമ്മൾ സ്റ്റഡി ചെയ്യുകയാണെങ്കിൽ ഇവിടെ നമുക്ക് ഇതിൻ്റെ മൂവ്മെൻറ്റ്, ഈ പാർട്ടിക്കിൾ അഥവാ ഈ ഹ്യൂമൻ മൂവ് ചെയ്യുന്നതനുസരിച്ച് അവിടെ പിക്സലിലുണ്ടാകുന്ന വേരിയേഷൻ അല്ലെങ്കിൽ പിക്സലിലുണ്ടാകുന്ന മൂവ്മെൻറ്റ് നമുക്ക് തീർച്ചയായിട്ടും കണ്ടുപിടിക്കാൻ സാധിക്കും. അപ്പോൾ അത്തരത്തിൽ ഈ ക്യാരക്ടറിസ്റ്റിക്സിനെ നമുക്ക് ആൻഡ് കോളനി ആയിട്ടോ അല്ലെങ്കിൽ ഈ ബീ സ്വാമിങ്ങുമായിട്ട് ബന്ധപ്പെടുത്തി നമുക്ക് പഠിക്കാൻ സാധിക്കും, സ്റ്റഡി ചെയ്യാൻ സാധിക്കും. അതാണ് ഇവിടെ ഉദ്ദേശിക്കുന്നത്. സോ സ്വാമിങ് ഈസ് ആക്ച്വലി ഹണി ബീ കോളനിക്കാണ് സ്വാമിങ് എന്ന് പറയുന്നത്. ആൻഡ് ബൈ നാച്ചുറൽ മീൻസ് ഓഫ് റിപ്രൊഡക്ഷൻ ഉപയോഗിച്ച് ഈ ഒരു കോളനി ഉണ്ടാകുന്നത്. ആൻഡ് ദി പ്രോസസ് ഓഫ് സ്വാമിങ് ഈസ് സിംഗിൾ കോളനി സ്പ്ലിറ്റ്സ് ഇൻറ്റു 2 or more ഡിസ്റ്റിങ് കോളനീസ്. അപ്പോൾ സ്വാമിങ്ങിൻ്റെ ഒരു പ്രത്യേകത എന്ന് പറയുന്നത് ഒരു സിംഗിൾ കോളനി സ്പ്ലിറ്റ് ചെയ്ത് രണ്ട് അല്ലെങ്കിൽ രണ്ടിൽ കൂടുതൽ കോളനികളായി മാറാം. അതൊരു പുതിയ ഗ്രൂപ്പുകൾ ഉണ്ടാവുന്നതാണ്. അതായത് ഒരു വലിയ ഗ്രൂപ്പിൽ നിന്നും ചെറിയ ഗ്രൂപ്പുകൾ ഈ സ്വാമിങ്ങിലൂടെ ഉണ്ടാകും എന്നുള്ളതാണ് ഇതിൻ്റെ ഒരു പ്രത്യേകത. അതുകൊണ്ടാണ് സ്വാമിങ് എന്നതിന് പറയുന്നത്. Okay, so moving to the next point. സ്ട്രീം റൺ ചെയ്യുന്നുണ്ട് ഇപ്പോഴും, കുഴപ്പമില്ല. സ്ട്രീം ബ്രേക്ക് ഉണ്ടോ എന്ന് ഇടയ്ക്ക് ഞാൻ സ്റ്റോപ്പ് ചെയ്യുന്നത് അതുകൊണ്ടാണ്. സ്ട്രീം ബ്രേക്ക് ആണോ ഇല്ലെന്ന് അറിയാം. സോ സ്ട്രീം ഇസ് കണ്ടിന്യൂയിങ്. So the population or swarm converges on the optimum by using the information gained from the each individual and referred to as a particle, as well as from the information gained by the swarm as a whole. Swarm എന്ന് പറയുന്നത് ഇവിടെ ഗ്രൂപ്പാണ്, എ ഗ്രൂപ്പ് ഓഫ് ബീസ് എന്ന് വേണേൽ പറയാം. The algorithm starts with an initial population that is randomly distributed throughout the design space. അപ്പോൾ ഇവിടെ റാൻഡമലി ഡിസ്ട്രിബ്യൂട്ടഡ് ആണ്. ഇപ്പോൾ ബീസിൻ്റെ എക്സാമ്പിൾ എടുക്കുകയാണ്. ഈ ബീസ് എന്ന് പറയുന്നത് റാൻഡമലി ഡിസ്ട്രിബ്യൂട്ടഡ് ആണ്. Then the algorithm starts with an initial population. അവിടെ algorithm സ്റ്റാർട്ട് ചെയ്യുന്നത് ഒരു ഇനീഷ്യൽ പോപ്പുലേഷൻ നിന്നാണ്. Then the position of each particle is then updated from one design iteration to the next using the following. So the position of each particle എന്ന് പറയുന്നത് ഇത് അപ്ഡേറ്റ് ചെയ്യപ്പെടുകയാണ്. ഒരു ഡിസൈൻ ഐറ്ററേഷനിൽ നിന്നും അടുത്ത ഡിസൈൻ ഐറ്ററേഷനിലേക്ക് ഇത് ഈ പറയുന്ന പാർട്ടിക്കിളിൻ്റെ പൊസിഷൻ അപ്ഡേറ്റ് ചെയ്തുകൊണ്ടിരിക്കുകയാണ്. Okay, let us see how this algorithm is working. So here this is a basic genetic algorithm. Create an initial population. So you have an initial population, so which is somewhat similar to a bee swarm. Then calculate the fitness from the initial population. After creating the initial population, calculate the fitness. Then select the parents. So ഇവിടെ ഫിറ്റ്നസ് കുറവാണെങ്കിൽ you have to select the appropriate parents. So always calculate the fitness, then select the parents. Then the parents have rankings, as you can see there it has rankings, and from the selected parents the children are created. As you can see, the children are created, and here once the children are created, the fitness is once again determined, and if the fitness is lower, the population or the creation of children will be in such a way that the higher rank population will be selected, and the parents will be selected in a random way, and it will be based on the selection which gives you the best characteristics. So actually the optimization is checked here. So this will be optimized to create children and which are fit, and the fitness is calculated at and this is repeated in a loop. As you can see, the fitness is calculated, and if the fitness is low, then the fitness has to be increased by selecting the appropriate parents, and the children here, these are the created children are optimized. And how we can show this in the mathematical expression? So using the update formula, xi raised to q plus 1 is equal to xi raised to q plus vi raised to q delta t. So xi raised to q plus 1 equal to xi raised to q plus vi raised to q delta t, where I refers to the ith individual in the swarm, and q refers the qth iteration, and vi raised to q refers to the velocity vector of the ith individual and the qth iteration. The time increment delta t is typically taken as the unity, and initially each particle is assigned a random velocity vector that is updated at each iteration using vi raised to q plus 1 equal to w vi raised to q plus c1 r1 pi minus xi raised to q by delta t plus c2 r2 p raised to g minus xi raised to q by delta t. ഇവിടെ ആക്ച്വലി ഈ ഫോർമുല എന്ന് പറയുന്നത് ഇതിനെ നമുക്കൊരു അപ്ഡേറ്റ് ഫോർമുല എന്ന് വിളിക്കാം. So actually, as you can see earlier, that x means the vectors, and how these values are calculated here. Xi raised to q plus 1 equal to xi raised to q plus vi raised to q delta t. So xi raised to q plus 1 can be computed from xi raised to q by adding vi raised to q delta t. So here I refers to the ith individual in the swarm, and the q refers to the qth iteration and Va raised to q refers to the velocity vector and of the ith individual in the qth at the qth iteration, and the time increment delta t is here the time increment delta t is typically taken as unit t. Initially, each particle is assigned a random velocity vector that is updated at each iteration using Vi raised to q plus 1. So, here can we calculate Vi raised to q plus 1 is equal to as you can see that Vi raised to q into delta t. So, the velocity, the random velocity vector is updated, and the updation is at each iteration by using Vi raised to q plus 1 is equal to Wvi raised to q plus C1 R1 Pi xi raised to q by delta t plus C2 R2 P raised to g minus xi raised to g by delta t. And these are from the earlier equation, might be remembering that the parameters earlier represents. So, the penalized objective function. So, p of x represents the penalized objective function. As you may see here, we can use pi here. Then where w is known as the inertia parameter, r1 and r2 is the random numbers between 0 and 1, c1 and c2 are known as the thrust parameters. Additionally, pi is the best point found so far the ith particle, and while p raised to g is the best point found by the swarm. The inertia parameter w controls the search behavior of the algorithm with the larger values, resulting in a more global search and smaller values, so in the region 0.5. So, actually you can see that maxima and minima values, these are the values here, 0.5, okay, then value 1, okay, this is the value 1, 0.5 and 1, this is the 0.5 values, and here the value is 1. So the result, the inertia parameter. So here w, the equation w is called as the inertia parameter. So here pi is the best point so far by the ith particle. So I think here is this pi is different from the earlier pi, that is actually pi of x. So p of x, rather, that is p of x. I think is since the same p is used there might be a slight difficulty that it can be misinterpreted as a penalty function. So here you can see that it's not a penalty function. So here pi stands for the best point found so far by the ith particle. And while p raised to q is the best point found by the swarm. So pi is the best point found by the ith particle, whereas the p raised to g is the best point found by the swarm. The inertia parameter w, here there is some inertia parameter w which controls the search behavior of the algorithm with large values of the region 1.4, resulting in more global search than a smaller values in the region 0.5, resulting in a more local search. So in between we have values, that is the maximum extremes are the larger values in the region 1.4, representing or requiring a more global search, whereas 0.5 region resulting in a more local search. The C1 thrust parameter indicates how much particle thrust itself, also referring to the cognitive memory, while C2 indicates how much the particle thrusts the group, also referred to as the social memory. So there are C1 and C2. As you can see the parameters here, C1 and C2. So these are called correspondingly called as the social memory, the cognitive memory. C1 is called as the cognitive memory, whereas C2 is called as the social memory. So actually the group has to trust either the cognitive memory, so according to the brain, whatever brain says, or the social memory. Here social memory corresponds to the memory of other particles, means based on the experience by other particles, so which is actually a social memory. So here C1 is the trust parameter, indicates how much the particle trusts itself. So here the particle trusts itself means it is it relies on its own memory, or which is called as the cognitive memory, or based on logic. Then C2 indicates how much the particle trusts the group. So suppose the group moves in one direction, the particle decides to move in the same direction, something like the B behavior. So if a group of B moves in a particular direction, whatever B follows will move in the same direction. So the literature recommends the values C1 equal to C2 equal to 2. Finally, P raised to G can be selected to represent either a local topology where the best point is obtained only from a small subset of particles, or a global topology where the best point is obtained from a swarm as a whole. So based on a global topology, the global topology will be based on the best point obtained from a swarm as a whole, whereas the local topology, here the best point is obtained only from a small subset of particles. So in terms of the parameters, the user needs to tune the values of W, C1 and C2 and decide on the number of particles in the swarm, as well as how many iterations to perform. So as in this particular equation, we can use as the parameters C1 and C2 and find out the velocity vector Vi raised to q plus 1. And in terms of parameters, the user needs to tune the values of W, C1 and C2 and decide on the number of particles in the swarm, as well as how many iterations to perform. Even this is the most basic variation of the algorithm. There are many variations that are much more complicated, and there are 5 problem dependent parameters that must be tuned by the user. So here we can see that the basic variation of the algorithm, there are many variations which can be thought of this particular algorithm. There are 5 problem dependent parameters. There are 5 problem dependent parameters that must be tuned by the user. The user must tune the values of C1, C2, R1, R2, and there are 5, as you can see, there are 5 parameters where the user can tune. Then the problem dependent parameter tuning is common to all evolutionary methods, and this is one of the major drawbacks associated with the methods. As you can see that you can change the value of parameters, that is say P1, P2, etc. Here can change, sorry, not P1, P2, we can change the value of C1, C2 or R1, R2, and this actually based upon the tuning. So the user should tune these parameters so that the best result is obtained. So problem dependent parameter tuning is common to all evolutionary method, and this is one of the major drawbacks associated with this method. Then the parameter particle swarm optimization. The particle swarm optimization algorithm, PSO algorithm, is inherently an unconstrained optimization algorithm. It is an unconstrained. So remember, the term unconstrained refers to there are no constraints. So PSO algorithm is an unconstrained optimization algorithm, and this is a common characteristics of most of the evolutionary algorithm, and is one of the major drawbacks associated with these methods. Many different constraint handling techniques have been investigated by researchers to deal with this problem, and the constraint handling techniques for evolutionary algorithms are classified by Koziel and Michael Wicks in 1999. And the techniques, these are the techniques that preserve feasibility, the techniques based on the penalty functions. So earlier we have seen about penalty functions. Then techniques making a clear distinction between feasible and infeasible solutions. Then there are other hybrid techniques, and here more recently Sees and Innocent 2008 classified the constraint handling strategies for PSOs. There is one is strategies that reject infeasible solution, also known as the depth penalty approach. Then strategies that penalize infeasible solution, also known as the penalty function approach. Then strategies that preserve feasibility. Then strategies that cut off at the boundaries. strategies that based on bisection approach, and strategies that repair infeasible solutions. So these are the various approaches for the strategies for PSOs. Of these, the approaches, one of the most popular is to use the penalty function approach, where the objective function is penalized for any constraint violation. So ഇവിടെ പെനാൽറ്റി സാധാരണ കൊടുക്കുന്ന എപ്പോഴാണ് അപ്ലൈ ചെയ്യുക? പെനാൽറ്റി എന്ന് പറയുന്നത് ഒരു കൺസ്ട്രെയിൻറ്റ് വയലേറ്റ് ചെയ്താൽ, ഫോർ എക്സാമ്പിൾ ട്രാഫിക് റൂൾ നമ്മൾ ബ്രേക്ക് ചെയ്ത് കഴിഞ്ഞാൽ നമുക്ക് പെനൽറ്റി അടിക്കും എന്ന് പറയുന്ന പോലെ ഇവിടെ കൺസ്ട്രെയിൻറ്റ് വയലേഷൻ നടന്നു കഴിഞ്ഞാൽ പെനൽറ്റി അടിക്കും. അപ്പോൾ എന്ന് പറഞ്ഞ പോലെ, സോ ദി ഒബ്ജക്റ്റീവ് ഫംഗ്ഷൻ ഈസ് penalized ഫോർ എനി കൺസ്ട്രെയിൻറ്റ് വയലേഷൻ. Penalty functions are popular because they have traditionally been used with the gradient optimization algorithms, are general in nature and easy to implement. Static penalty parameter penalty parameters like that of equation 6 are typically employed. So as you can see in the equation number 6, here use the penalty parameters. So we use the penalty parameter equation 6. Let us revisit equation number 6. Yes, this is equation number 6, and where you use the penalty parameter p of x, and this the penalty function is p of x, and the penalty parameter is rp. Here rp is the penalty parameter. So static penalty parameters like that in equation 6 are typically employed, but more advanced techniques in which the penalty parameters are dynamically tuned during the optimization have also been developed. Example, Poon and Jacquin 2007, and Hamida and Schoenauer 2000, and Barbosa and Limongs 2003. A recent technique for constraint handling is a bi-objective approach similar to that used by Fletcher and Leif 2002 for gradient-based optimization. So there's a recent technique for constraint handling, and it's a bi-objective approach similar to that used by Fletcher and Leif for gradient-based optimization. A bi-objective method, so it's actually there are two techniques earlier we discussed. One is the one-dimensional approach, and the second one is the bi-objective optimization, and which is using more than one dimension. Then a bi-objective optimization problem that minimizes both a measure of the constraint violation and the objective function is considered. So in a bi-objective optimization problem, it minimizes both measure and the constraint measure of the constraint of violation and the objective function. So example can be seen in Surrey and Radcliffe in 1997. These are the papers referred here, Venter and Hafka 2008. Then next is the deterministic algorithms. So there are also many deterministic algorithms developed specifically to solve global optimization problems. An excellent survey of global optimization algorithms is provided by Neumeyer 2004. Many global optimization algorithms are specialized to solve only a narrow class of problems. So ഇവിടെ ഗ്ലോബൽ ഒപ്റ്റിമൈസേഷൻ പ്രോബ്ലംസ് പറയുന്നത് ഇവിടെ സ്പെഷ്യലൈസ് ചെയ്തിരിക്കുന്നത് കുറഞ്ഞ പ്രോബ്ലംസ് സോൾവ് ചെയ്യാൻ മാത്രമേ സാധിക്കത്തുള്ളൂ, ഗ്ലോബൽ ഒപ്റ്റിമൈസേഷൻ പ്രോബ്ലം. So there are also many deterministic algorithms. ഇവിടെ deterministic algorithms എന്ന് ഉദ്ദേശിക്കുന്നത് these are specifically developed to solve global optimization problem. അത് ഗ്ലോബൽ ഒപ്റ്റിമൈസേഷൻ പ്രോബ്ലംസ് സോൾവ് ചെയ്യാൻ വേണ്ടിയിട്ടാണ് ഡിറ്റർമിനിസ്റ്റിക് അൽഗോരിതം ഉപയോഗിക്കുന്നത്. And an excellent survey of global optimization algorithms is provided. So here we can see that most of the global algorithms are specialized to solve only a narrow class of problems. And one popular general purpose deterministic global optimization algorithm is the direct algorithm, Pertunen and Stuckman. So one of the global optimization algorithm is the direct algorithm by Jones, Pertunen and Stuckman. And the direct algorithm makes use of the Lipschitz-Sien optimization to locate the promising subregions in the design space, and each of these subregions is then further explored using the local search technique. So in the direct search algorithm makes use of Lipschitzian optimization and to locate the promising subregions in the design space. So I think by this time you mean you can understand what is meant by design space. Any something like in a pattern recognition problem, the two-dimensional space, that is xn consisting of x and y, coordinates x and y, this is the design space. And the direct algorithm makes use of the Lipschitz optimization to locate promising subregions in the design space. So you can promising subregions in the sense particular locations in the xy two-dimensional space, and these subregions is then further explored by using the local search techniques, and the subregions can be further explored. So instead of searching for the entire two-dimensional space, particular regions or location in the two-dimensional space can be searched by using local search technique. Then let us conclude this. In the concluding remarks, we see that this presentation has provided a short overview of the optimization techniques typically encountered in engineering optimization applications. So we have seen various engineering optimization applications where different optimization techniques are applied. The techniques were classified as either local or global algorithms. Both constrained and unconstrained optimization problems were considered. The designer should be aware that no single optimization algorithm exists that will solve all the optimization problems. Some knowledge of the different algorithms available will help to select the appropriate algorithm for that problem at hand. So we have to use a different approach for solving different problems. So some knowledge of the different algorithms available will help to select the appropriate algorithm for the problem at hand. A few guidelines for algorithm selection are: local algorithms are well suited for optimization problems with many design variables, say more than 50. If there are more than 50 design variables, then we have to use a local algorithm. In cases where the analysis is computationally expensive, when numerical noise is not a severe problem, and when the gradients are readily available, and when local minima is not an issue. So here local algorithms can be well suited in cases where there are more than 50 variables, and also in cases where there is analysis is computationally expensive and where numerical noise is not a severe problem, and also when the gradients are readily available, and also when the local minima is not an issue. Whereas a global algorithm are well suited for optimization problems with fewer design variables, that is less than 50. When the design variables are less than 50, global algorithm will be suitable. Where the analysis is computationally inexpensive, so in the global search the analysis will be computationally inexpensive. For discrete and combinatorial optimization problems, and the analysis is computationally inexpensive for discrete and combinatorial optimization problems when numerical noise is severe, in cases where gradient does not exist, and when the objective and or the constraint function are discontinuous, and also when the global optimum is required. And where once again just looking at the global algorithms and the application of global algorithms, the global algorithms are well suited for the optimization problem with fewer design variables. So when the design variables are less than 50, we can use global algorithms, and where the analysis is computationally inexpensive. So for inexpensive computation also global algorithms are useful, and for discrete and combinatorial optimization problem again global algorithms are useful. And when numerical noise is severe, so where in problems where numerical noise is severe, we can use global optimization, and in cases where gradient does not exist also, we can use global algorithm where the gradient does not exist. And when the objective and the constraint functions are discontinuous, so when the objective or the constraint functions are discontinuous, then we can use the global algorithm, and we can use the global optimum. So in general, the rule as a rule of thumb, we can consider to the global methods. In general, a rule of thumb is to consider the global methods only in cases where it is not viable to use efficient local search. So first we have to try for local search, if we see that this is not successful, then we can use the global search or the global methods. And with this we conclude the topic on optimization techniques. Thank you for watching the video.